those by building them out of a transparent smart contract.
So what is the class and how is it different or smaller, transparent?
It's a class that's parameterized by a user function, which is just a mapping from up to n inputs for some n of user inputs to user outputs.
So can any transparent smart contract be made into a private?
No, no. Not in general. All we do is that for a class of private smart contracts that have this, they're parameterized by this function, and they do what that structure is, like they collect commitments to inputs at some time, and then after that time they reveal them to a manager and then wait for the manager to go ahead, and then at the end they give the private outputs to each party. We can realize that class of applications.
Can you do applications in which there is more than one round of communication between the parties?
Not in what I've covered. That would be a straightforward extension. I say straightforward. That would be a good future work extension.
Because that seems like the first thing you couldn't do, like what you're saying, commitment, run, decommit.
Yeah, that's the only.
That's only a one round, one shot
Correct.
exchange. Okay.
Just to follow up on Bobby's question, it sounded like you're saying that contracts that are private are ones that perform the steps that you mentioned earlier, that do the commitments and everything else. But couldn't you compile a transparent contract to do those steps as inserted by the compiler?
So, sorry, say it again. If you could break this into a sequence of steps.
I'm saying that I thought your answer to Bobby was, if I'm given an arbitrary smart contract, which I'm thinking, an interesting thing about the contract is the function that I'm going to run. It takes a bunch of inputs and then produces an output, and the inputs come from each party. And you said, well, no, not everyone can be, every transparent one can be private because they don't necessarily send commitments and do this encryption step and everything else. But I'm saying, why can't you compile all that work in from an arbitrary?
No, that's not the problem, right?
So what is the problem?
The problem is that the structure has to be input, compute,
Yeah.
output.
Exactly.
Right? The commitment is just the way to provide the
I see.
input.
Transparent
That's why I was
contracts are-
asking if it was input, compute, and then further input based upon the compute, for instance.
I see. So
But
that
then that
can
would
be
be
transparent,
captured.
but it can't be private.
Well, at least not by the structure that it has.
I see.
So one way of thinking of this generalization is that our final model includes not just Bitcoin, but also Ethereum and Zero Cash, which is a private transfers, but no programmability. It's just you can send private money to someone else. These are two of the leading proposals for state-of-the-art cryptocurrencies. Our model generalizes all of these, and then it also provides a new data point because it provides both privacy-preserving payments and this kind of programmability that Ethereum does.
So just by the last discussion, you have Hawk too far down. Should it also be, is it also too far right?
Yeah, I see what you're saying. We do provide a model of what the privacy preserved in payment says. It is not exactly what Zero Cash provides, but it is equally private. Zero Cash has an extra feature which allows you to have long-term private keys. So you can send a message to someone by their public key without even having to talk with them out of band to like generate a new key pair for them. And so you can approximate what Zero Cash does, but it requires extra interaction. So yeah, technically it's too far right because there's a tiny thing that you can do with Zero Cash that requires extra interaction in protocol.
But if you just wanted private payments in Hawk, still need a trusted manager or no?
No, you don't need a trusted manager for payments.
You never need the trusted manager, right? You could just do multi-party computation of all of the people who are doing it. This is just a.
If you want payments, and the payments are going to, you don't want, even if all of the parties to the contract go bad, you don't want them to be able to inflate money.
Well, I guess let me rephrase the question then. So without MPC, do you need the trusted manager for private payments at all?
You don't need the trusted manager for privacy payments, no. If you don't try to use the contract feature with collecting lots of inputs and moving lots of outputs, then it just reduces to Zero Cash.
Then that's just a commitment.
Huh?
That's just a privacy hiding commitment or something?
Yeah, plus a zero knowledge proof.
Well, I guess
that
the payer would act as a manager or something like that?
You can do that too, sure. We include a formal model of Zero Cash and then build on top of that with extra functionality. So it's not like you have to kind of shoehorn it into rounds of the protocol. You just use the extra points that are just like transfer messages.
So coming back to Bob's question about reactive functionalities, could you just take the output of the manager as you will take it normally and just do another commitment on the next input and like run it sequentially, what you did like.
I
first,
think
right?
that would be an effective way to do it, yeah.
Okay.
I mean, say I think it's straightforward, that's kind of, the approach.
So this is how we probably do it?
Yes.
Okay.
Have the manager keep commitments to kind of state. Let me mention a bit about the implementation that we did of this. So I say that we created this programming language, but it's a little simpler than that sounds. We used an existing tool called Pinocchio, which takes C code and generates an arithmetic circuit implementing that C function. Arithmetic circuits are the native underlying language for existing zero-knowledge proof systems. So this output of this compiler represents the user-defined portion of the application. All right, the next step is to extend the user-defined application with this extra layer of cryptography implementing the protocol. And let me at this point say that all of the work done to make this protocol as efficient was entirely done by Ahmed, and this required a ton of really good engineering and inventive stuff. So we need to include an encryption scheme and commitments and pseudo-random functions and other cryptography. And in order for these to be efficient when implemented as a zero-knowledge proof, you need to have crypto schemes that are efficient when they're implemented as an arithmetic circuit. And so in the Oakland paper, we have an efficient particular instantiation of all of these. Also, Ahmed has a later work that's currently in submission. I guess we'll hear back about that in a few days. So that includes a systematic exploration of lots of different potential concrete instantiations and benchmarks of how efficient they are. So I want to be clear that I'm not taking credit in my dissertation for any of the concrete details of the protocol or what make it efficient. Just the formalism and proofs about that. Finally, after having this augmented circuit, the final circuit that includes our protocol-specific things as well as the user application is fed as input to libsnark, which is an existing library for generic zero-knowledge proofs that's really practical. And just to summarize what our performance figures with this, in our test example of 100 users in an auction, the cost of this for the manager to do that last step is only 3 minutes. This is across 4 cores in parallel. And for a user part, this is also scales linearly with the number of users. For the users to do their initial zero-knowledge input when they do their commitments only takes 50 seconds on a single core. And that work is independent of the number of users that are doing it. The main overhead in this protocol is just producing these zero-knowledge proofs. There is other crypto in the protocol, but it has a negligible impact on performance. And probably the most important factor is what would be the cost of validating all of these zero-knowledge proofs, because this is something that would have to be carried out by all of the nodes on the underlying cryptocurrency network that's implementing this. And for all the zero-knowledge proofs in the protocol, it takes 1.5 seconds to verify them all.
Well, would you do better here by using tailored protocols instead of general?
Yes, I believe that we would be able to use a tailored protocol to an application. That would be then a lot more efficient rather than using this generic. Because we're building the contracts on, sorry?
I thought I read something which said tailored protocols don't do better. I was thinking.
Yeah.
Eventually they don't.
Eventually,
Depends on the application.
in special cases, there are.
No, I mean, 50 seconds looks high when you could do a zero-knowledge proof with all the mount commitments, in a second.
Sure. So again, we're building on top of an underlying
No,
scheme
I
of zero cache,
understand.
and we could tailor a particular application and a particular eCache application, eCache protocol for that one application. But I think that having one eCache and then all of these applications on top, I think.
I mean, 50 seconds seems long to me, but I mean, I understand the benefit of having a generic solution, but
Yeah.
but if auctions became popular all of a sudden, you might want to rewrite it.
A really popular place for doing auctions is like bidding in real time on which company gets to display an ad in your browser, and like you can't do that if it takes 50
Yeah.
seconds. So yeah, it depends on the application whether or not this is tolerable. Okay, so let me wrap up. So in summary, what I've done is build a model cryptocurrency protocol where I can say what the guarantees and assumptions are from the whole stack, beginning with a model of the underlying communication network through the consensus protocol and then the application layer. For the consensus protocol, I factored out this key primitive of scratch-off puzzles, one instance of which is embodied in Bitcoin, but then I showed how to make other instantiations of it that have these extra benefits. And then finally, I showed how to, instead of just having a digital currency application, to generalize it to a larger class of applications, and in particular provide protocols for new privacy-preserving applications that extend past what you could previously do with cryptocurrencies. I have done a bunch of work, especially in collaboration with other people, during the time that I've been here that I didn't include in my thesis. Probably these cover into a couple of categories. One of these is system side. I've done some of this with Bobby, including measurements and simulations of the actual cryptocurrency systems today, and scalability issues with them. Also with Mike, I've done work on programming languages and cryptography to make it easier to build crypto protocols, and other issues about security when doing Ethereum-style smart contracts. And I've also had a really good time working with folks at Princeton and building an online course, and my textbook is now on Amazon, so you can buy this. There's also a free PDF, so you don't need to buy it unless the book turned out really well, so that's why I'm showing it off. The overarching question that I'm trying to address, this work is really just the beginning because I'm able to show some kinds of improvements and provide some structure with some kinds of applications, but there's a lot more that we would like to do. So in general, the question that's motivating me is, can we design secure public infrastructure systems that anyone can use for as broad classes of applications as we can, and even under really difficult environments where you don't assume that you just have a trusted administrator in charge of everything. And so this is the overarching question that I'm going to begin working on when I start as an assistant professor at University of Illinois in the Security and Privacy Lab this fall. Okay.
Assuming everything goes well.
Assuming everything goes well today or shortly after today, but found the time. Okay, so I'd like to thank all the people that I've worked with over the few years here, and I'm done. Thank you all.
Any questions from the audience?
Yeah.
Is there any ability for Ethereum or Zero Cash to adopt some of the lessons you displayed today into their?
It's really difficult to upgrade Bitcoin, especially with experimental stuff, because there's so much money at stake that people are justifiably very concerned. I should point out that Greg works at Blockstream and is a UMD alum, so he works for one of the companies that is most in charge of upgrading Bitcoin development. So you're welcome to
Work with smart people.
You work with smart people. That's Ethereum has expressed interest in adding support for the zero-knowledge proofs that I've talked about, which would be a way of adding these kinds of applications on top of it. And it's likely that altcoins will be able to experiment with these non-outsourceable puzzles, and if they can solve any of the issues with integrating them there, then it might be something that Bitcoin could eventually adopt.
How does Ethereum have to change in order to incorporate anything that we talked about?
The zero-knowledge proofs, I mentioned that the verification takes, like 1.5 seconds for 100 of these. You can't implement that in the Ethereum programming language, though. It would be much slower. So we would essentially need to just add an opcode to support verification. That's what would roughly be the approach for that. I think that Ahmed actually had at one point a working prototype of an added opcode into Ethereum that ran acceptably or something.
Yeah, we had this in a very simple opcode edition of our Ethereum.
I was wondering, in the digital cash stuff that's involved here, there's presumably some D-logs involved. How secure are these?
Sorry, say again?
There's some discrete logs involved or something that are, it's behind.
Yeah, like underlying signatures.
How
It's
big
even
are
a-
the, what's the bit size of these things now? 'Cause-
Correct, yeah.
Which
For the
For-
Bitcoin's easy
like,
to
let's say
say.
Bitcoin.
Name Bitcoin.
I mean, there's been such progress in discrete logs in the last couple of years.
Yeah, a lot of people actually talk about post-quantum cryptography here, so eventually the
Well,
elliptic
even forget
curve-
post-quantum, I
yeah,
mean,
just breaking the elliptic
just-
curves.
I mean, there was a 4800 discrete log done a couple days ago.
That was in a prime field, not another.
Well, yeah, it was a prime field. It was
Yeah.
a security 3, but still. I was just curious what kind of discrete logs are used in Bitcoin, do you know?
I mean, it's using ECTSA, so it's this
Yeah,
particular
okay.
algorithm. The curve, yeah, the curve that's used is,
Same in
yeah,
Ethereum.
it's a NIST curve. It's
the
not
big,
the most
it's the biggest
popular
NIST curve.
Sorry?
Biggest NIST curve.
Is it the biggest? I don't know.
It's
the-
256 bit.
Oh,
Yeah, the
It's
signature-
128 security.
Oh, so I'm not going to invest in Bitcoin then. I mean, it's getting close, you know.
Yeah, I mean, the point is, right, the hash computation is 2 to the 70 minutes, and it's 2 to the 128 to break the discrete log, so.
Well, that's what they thought of this one that was just broken. They said it was advertised as 128-bit security.
Oh, really?
Yeah, because there's an elliptic curve, and then you multiply by, it was 800 bit.
I didn't hear about this actually. Who did it?
Manassas, Waterloo. Yeah, and it was multiplied by 6, they do the pay pairing. And, yeah,
Huh.
I just got the email yesterday.
One interesting, a really interesting question is if it's so difficult to upgrade Bitcoin and the stakes are so high and it can't handle, service outage and so on. So is there a way to gracefully upgrade to the cryptography? And what I think works is that you can add new signatures, and then it doesn't matter if you crack old signatures as long as you don't have to upgrade the hash function, and the hash function is still secure. Then the log of what took place is, can be assumed valid.
Mhm.
So you could even gracefully upgrade the signatures and only there's a feature that people are careful about, which is if you haven't spent money yet, you don't reveal what your public key is. You only reveal a hash of your public key. And this potentially prevents people from getting a head start on signatures, which they might be able to if they saw the public key.
And so the hope is soon in Bitcoin to upgrade to Schnorr signatures.
Okay.
Yeah, pretty straightforward upgrade.
Yeah.
Why is that any better?
More compact.
Sorry, say again what the
Schnorr signatures. You get native multisig, so you can do a smart contract between us two. If we play along and are nice to each other, then we just pay out to what looks like a one of one.
Schnorr signatures
address.
have like an aggregation
Yeah.
feature, so they algebraically combine religiously, use a single challenge value and then respond to that one challenge, so it reduces the size for a bunch of signatures on the same message, which you can't do.
It was patented until 2008, which is probably why Bitcoin didn't use it.
Yes.
This is kind of orthogonal to your thesis, but if you adopt a proof of work model, are there privacy concerns with that? Like, say I'm winning a lot of the block rewards, and I don't want to divulge that I have so much to stake inside the system.
Yeah.
Is that a privacy concern that exists?
I think so. It's definitely not something that I model. It would be reasonable to, first of all, most mining pools advertise, they put a little message in blocks that they find saying, claiming it, so that's how you could build that kind of pie chart like I showed you. You could, if you wanted to, the members of mining pools, though, are effectively behind a shroud of the mining pool that they're operating in. And if you wanted to, you could just generate a fresh address every time you mine. So I don't think there's anything that makes you private, and whether or not you should be private and why you should matter, I don't think it's explored, but I think that's interesting. That's right.
Is there a Pandora's box with enforcing privacy, that the moment that you start enforcing it strongly, that people with power can maintain that power, increase their power, and do bad things because they're able to do it privately?
Yes, it's already possible even using Bitcoin if you're very careful about it and diligent about it to use mixes and various techniques of hiding your tracks. So, one heuristic is to say, well, this is still better to, improve privacy because criminals already get the benefit of privacy. It's just right now people who don't go out of their way to do it, are leaking their information.
I guess I'm thinking of things not even, lots of the time privacy concerns are motivated by stuff like anonymity and repressive regimes or something like that. But I'm thinking of the thing that lots of liberals are really excited about, which is income inequality, where big corporations have tons of power and they just continue to distance themselves from normal people, and that a huge successful network like Bitcoin will just enable them to do that even more and be able to deny that they did anything.
That's a really important question that people are talking about in this community a whole bunch. My view on that is that this doesn't change any of the ordinary roles that existing social institutions are supposed to play. So what the technology allows you to do is to choose as a user whether you're going to be private or not. It's totally reasonable for a company in a regulated business environment to have to disclose, to have like a handful of published keys where they receive all their invoice payments and be able to reveal to auditors what they use. And you can still do that even with the privacy preserving things. You can reveal, and if you fail to reveal all the inputs that came to your address, then you get audited and shut down or whatever. So it does, just like cash, provide the technical ability to not reveal where your income sources were, but in a regulated business environment, the big players could just as much be required to.
I guess I feel like it's a bit of, so I understand what you're saying, but it's a bit of an evasive answer to say that it's the same social institutions. I mean, the reason that before Napster we didn't care about people making copies of tapes was that scale was not an issue. But the moment that you have the internet and you have this decentralization of copyright infringement, then all of a sudden it was costing big dollars, right? So the same thing is true. You can't easily ship pieces of paper all over the world, but you certainly can push around lots of transactions on Bitcoin.
Yeah, absolutely. I don't know. That is a good question. I don't have a further rebuttal to that.
So So I guess if the audience doesn't have any more questions, you can leave and we can, the committee can stay behind.
Waterboard.
What's that?
Waterboard in private.
Andrew, do you want me to turn this off or?
Yeah, okay. Thank you all.